going to do one more, what's it called? Related rates examples. So let's do this. Okay, another example. So let's say that water is draining from the bottom of a cone-shaped funnel at a rate of 0.03 feet per second. The height of the funnel is 2 feet. And the radius at the top is 1 foot. The question is, at what rate is the height of the water in the funnel changing when the height of the water is half a foot? Okay, so there's like a lot to pick apart here. Usually you go through and you read it, and you have to like digest it and draw your diagram, figure out what you're doing. Okay, so we're draining through a cone-shaped funnel. So first I'm just going to draw our cone-shaped funnel. Shit, that's not what I wanted. Cool. So you get this cone-shaped funnel. Okay. What do we know about it? The height of the funnel is 2 feet. So from top to bottom, 2 feet. And we know that the radius at the top is, what was it? 1 foot. Okay, so we have some dimensions of the funnel. Now, what happens is, as the water goes down, like you have a water level, right? So does it make sense? Like the water is not always all the way at the top. Like as you drain, it's going to go down. So what they're saying is like, hey, there's some height for the water at any given moment. So the height, let's call it this. So you have this height of the water, and we want to know how that height is changing when there's a half a foot of water. Right? So it's draining at some constant rate, and it's going down. Now here's the interesting thing. So because it's draining at a constant rate, is the height going down faster at the top, or is the height going down faster at the bottom, and why? Yeah, so what happens is, like, because the rate at which it's draining is constant, because it's wider at the top, that fixed amount of water going out drops it lower, because the height can be smaller because it's like draining out a disc. The height has to be bigger as you get smaller. It's sort of like, has anyone ever seen in a sink, if you fill it, the water level drops quicker at the bottom because it's draining at a constant rate, because when it's more open at the top, that constant rate of draining, it doesn't give as much height drop, basically. Okay, so we want to know at what rate is the height of the water changing when the height of the water is 1 foot. So let's identify what we've got here. The water is draining at a rate of 0.03 feet per second. That's the volume. The water, we measure the amount of water by the amount of volume. So the one that we know is dV dt. Now we want to know how the height of the water is changing. That's dH dt. Okay. And the height of the water is this variable right here. Like the h refers to how high the water is, and as it drains, h is getting smaller. So you might be looking at this and you're like, wait, so what do I need? I need a variable that relates the volume of the water to the height of the water. So you have to start asking yourself, like, well, do I know what the volume of a cone is? Hopefully you do, and I think it's 1/3 pi r squared h. Okay, so you look at this, you're like, oh, this is good. If I take the derivative of v, I get dv dt. If I take the derivative of h, I get dh dt. But you have that extra variable r in there. So what do we do with the extra variable r? What do we do with the r variable? And what we're going to do is get rid of it. And the way you get rid of it is that you realize that if you look at this cone, let's draw a height thing down here, that you get a, what's it called, a right triangle. Hopefully you can see this right triangle that I'm drawing. This right triangle has the height of the cone, and then you know on the cone on the outside it slopes, that's your hypotenuse, and then the base is going to be that radius on top. So what you get is a big triangle that's 2 units high, because that's how tall the cone is. And on top it's 1, right? Because the radius is 1 at the top. And what you can draw is a similar, smaller right triangle that is where the height of the water. So the height of the water at the moment we're interested in is 1/2. Now obviously these aren't to scale. So that's 1/2, and we're going to call this r because we don't know what the radius of the water is right there. Now what you can do is you can set up an equation. And I guess actually what we really know is that, oh, actually, my bad. Sorry. We're not going to plug in 1/2 right here yet. We're going to leave h. This is the height of the water. I'm not going to put 1/2 there because the water is variable. It's draining, right? It's not 1/2 feet forever, so we have to leave the variable h. Same thing for the variable r. As it drains, the radius gets smaller, so I need to take that into account. But what I can do is I can set up this equation that says h over 2 is equal to r over 1. And I can solve for the r variable. Oh yeah, if I just get rid of the... it's r over 1 is just r. So r is equal to h over 2. So what I'm going to do is take my volume equation now and plug in wherever there's r and h over 2. So I'm going to get the volume equals 1/3 pi, my r is h over 2 squared times h. Now I only have volume and height, the 2 variables that I want to relate. So let's simplify this. If you square it, you get it over 4, so you're going to get pi h cubed, 3 times 4 is 12. So 1/12 pi h cubed. So my first step was to get rid of the r variable. I only want to have v and h, the 2 variables that I want to relate. So how did I get rid of that? Well, I realized that by looking at the cone, I could set up similar right triangles, right? Remember, there's the rule which says the ratio of sides in proportional triangles can be set equal to each other. So I put h over 2 equals r over 1. That gives me what r is. Okay, now, how did I get 1/12? Because if you take the h over 2... oops, okay, what happened to my pen? sorry, my bad. If you take the h over 2 and square it, you get h squared over 4. And then notice there's this 3 over here. And 3 times 4 is 12, yeah. No problem. Okay, so now what you can do is you can take the derivative on both sides. So on the left, I get dv dt equals the derivative with respect to t of 1/12 pi h cubed. Now the pi over 12 can be factored out, so I get pi over 12 times the derivative with respect to t of h cubed. And this is where the implicit differentiation comes into play. So you get pi over 12 times 3h squared dh dt. So we can simplify this. Left hand side is still dv dt. The 3 over 12 is going to give us 4 on the bottom, so you get pi over 4 h squared dh dt. And what you can do is plug in the numbers. We were told at the beginning that dv dt was 0.03 cubic feet per second. The pi over 4 is just pi over 4. But the h at which we are wondering about when the water is draining was half a foot. So you put half a foot quantity squared. And this will allow us to solve for dh dt. If we multiply that through, we're going to get pi over 4. Now, if you take the 1/2 foot and square it, you're going to get 1/4 of a foot squared. Over here, you still have the 0.03. And actually, let's rewrite the 0.03. That's 3 over 100. Feet cubed per second. Okay, to solve for dh dt, I need to divide both sides by, so that's going to be pi over 16. Right? This whole thing here becomes pi over 16. So instead of dividing by pi over 16, let's multiply both sides by the reciprocal to get it to cancel. So we're going to multiply by 16 over pi 1 over foot squared. So my pi over 16 foot squared will cancel with my 16 over pi foot squared, leaving me with dh dt. Now on the left hand side, the foot squared will cancel with 2 of the cubic feet, leaving me with just feet per second. And then there's some more canceling that can be done. The 16 and the 100 are both divisible by 2. That would be 8 over 50. Those are still divisible by 2. 4 over 25. Do 25 and 4 have any common divisors? No. So that will leave me with 12 over 25 pi feet per second. So that's telling me how is my... Oh, there should be a minus here somewhere. Oh, this minus point... This should be minus 0.3. So it gives me negative because we're losing water. So this is telling me that my height is decreasing by 12 over 25 pi feet per second. If you turn that into a decimal, what is that going to be? 12 divided by 25 times pi. Turn that into a decimal. That's, yeah, negative 0.15 feet per second. Let's multiply that by 12 to get in inches. That's 1.8 inches per 1.8 inches per second. because this was feet per second. So if we're draining at a rate of 0.03 cubic feet per second, the height at 1/2 feet is going down 1.8 inches every second. So in other words, like if you were watching it drain at that moment, after 1 second, you would see the height of the water go down by about 1.8 inches. So in a second, you'd see it go down 2 inches approximately. To give you an idea of like